It's very early in the morning, but thanks a lot for coming this early. So our first speaker today is Omri Weinstein. He has a lot of work on self-probe lower bound and very recently has some very exciting series of work on connection between dynamic algorithm and machine learning. And so that's what he's going to talk about today. So Omri, please take it away.
Is that okay? Thanks everyone. Thanks for the invitation to the organizers, and thanks for waking up this early. So the purpose of this talk is to highlight some of the connections and the role that dynamic data structures play in large-scale machine learning and deep learning, which seems to be kind of taking over our lives. And in particular, to focus on two important algorithmic primitives which form some of the major bottlenecks to large-scale AI and machine learning. On the technical level, my goal is to describe a fairly general dynamization technique which may be useful for various online matrix problems, and to describe a lower bound technique which kind of relates fine-grained complexity to numerical linear algebra. So let's start. So two of the most popular primitives in almost any empirical risk minimization problem or machine learning task you can think about are the problems of least square regression, aka approximate linear systems, and the problem of matrix vector multiplication. So in the first problem, we are given a tall, over-constrained data matrix where you can think of the rows as the training set examples, along with a label vector B, which is kind of the classification of each example. And our goal is to approximately solve the underlying linear system. Of course, because the matrix is usually tall, usually the number of examples is much higher than the dimension, it's accumulating over time, we cannot hope to solve this linear system exactly. So the goal is to solve it as good as we can, to approximately solve to find the best linear fit, the hyperplane that minimizes the L2 loss. And of course, this is a classic century-old problem. And it's really the bottleneck, least squares regression is really the bottleneck of high-dimensional statistics, support vector machine, kernel methods, and many more primitives in machine learning. And as we've seen in Richard and Jan's talk over the past couple of days, least squares regression is really the key step, most computationally expensive step in second-order Newton methods, such as interior point methods, Newton natural gradient descent, and so forth, where remember that IPMs reduce a problem of conic optimization to a sequence, to a short sequence of linear system solves, which are essentially least square regression subroutines. In the second problem of online matrix vector multiplication, our goal is to pre-process a matrix. Let's say it's square for now, it doesn't have to be, but just for simplicity. So we need to pre-process this matrix into a cheap data structure so that we're able to answer an online, possibly adaptive sequence of matrix vector multiplies much faster than the quadratic naive time, which is just reading the matrix, right? So n squared is just the runtime for reading the matrix. And, you know, I don't need to praise the importance of matrix vector multiplies. It really arises in many, many primitives in data analysis, from power methods and singular value decompositions, conjugate gradient algorithms, Kirillov methods, in Bregman projections, mirror descent, kind of first order optimization methods, and perhaps most notably in the training and inference process of deep neural networks, where matrix vector multipliers are basically the way to implement the forward and backward propagation of the signal throughout the network. And just to, an anecdote on how severe this primitive is, how severe this operation is, the prophecy of Facebook's AI report from about a year ago, is that within 3 years, so by 2026, the energy cost of training a state-of-the-art NLP or vision model, let's say those BERT models or transformers, will be equal roughly to the monthly carbon emission of New York City. So this is for training one model, right? So this is really a showstopper. And on a tangent line, this makes you wonder, what's so holy about matrix multiplication, right? Can we replace matrix multiplies by a cheaper bilinear operation, which is equally as expressive for human-related tasks and is much cheaper to compute? But this is really a topic for a different talk. There's evidence that this is actually possible, and I'm happy to discuss this offline. But back to the OMV problem. So the reason for why one might hope to design a data structure with sub-quadratic query time for this problem is that if the queries VI were given in advance as a batch, not one by one, then we can actually solve this problem much faster than n squared amortized. We can just use Strawson's fast matrix multiplication to produce all the products in roughly n to the 2.37 total time, which amortized per vector is something like n to the 1.37. This is much, much faster than n squared time. But unfortunately, all fast matrix multiplication techniques crucially rely on recursive and tensoring batches of both matrices M and V. So they crucially rely on batching. And these techniques, all of them without exception, completely break once the right matrix arrives one by one, column by column. Does that make sense? And indeed, a beautiful conjecture by some of the organizers here, Hensinger, Tachapol, Danupon, and Sebastian, postulates that this is not a coincidence, that this phenomenon is inherent to fast matrix multiplication. They conjecture that, in general, for the online problem, you cannot get truly sub-quadratic time per matrix vector multiply. Does that make sense? And they postulate this is true even if multiplying not over the reals, but over the Boolean semi-ring. This is important for graph problems. And this conjecture is quite subtle. So it turns out you can shave off sub-polynomial factors. But if this conjecture is true, it really implies kind of holy grail lower bounds on dynamic data structures, in particular that we can kind of only dream about. For example, it would imply a tight root n update time for dynamic directed reachability, and for many other like range median problems and other dynamic problems. But in our context, what this conjecture implies is that if we do hope to achieve sub-quadratic amortized time in the online setting, then we better impose some structure on the matrix V or resort to some small approximation or both. And one such structure you might hope to impose is, for example, an algebraic structure. So if M has, let's say, an FFT structure, then you can multiply M by VI in, let's say, n log n time. Another class of structures you might hope to impose is a geometric structure on M. And an important subclass of geometric matrices are known as kernel matrices, where these are n by n matrices, which are dense and full rank, and yet they are completely defined using n points in some low-dimensional space, Rd, where the ijth entry of the matrix is some analytic function of the distance between I and j. Does that make sense? Question? All right, and some examples for the function f are the Gaussian kernel, where the function is the exponentially decaying function, or the Laplace kernel, which is 1 over L1 norm. and so forth. And this class of matrices is extremely important, has a special role in the context of machine learning because a lot of machine learning algorithms, most notably support vector machines, really depend not on the raw feature space, which could be gigantic in modern applications, but only on the distances, only on the inner products between the points. And this is basically the core behind the kernel trick or kernel methods, if you've heard in machine learning. Questions about this? So really, multiplying kernel matrices by vectors is something we care about. And perhaps surprisingly, it turns out that if the function f is decaying fast enough, then indeed you can do this in n polylog n time, even though the matrix is dense in full rank. So this is known as the fast multiple method and was declared as one of the top 10 algorithms of the 20th century, and I hope to say something about this towards the end. Questions about these two primitives? All right, so the point is that in the static setting, both of these problems are kind of very well studied and pretty well understood. They're essentially settled. However, in modern applications, data sets are usually very rapidly changing, either by nature or by design. And in the context of machine learning, if our training set evolves in an online fashion, you know, movie ratings being uploaded to Netflix's, server and so forth, of course, we would like to avoid retraining the model from scratch. We don't want to perform learning from scratch. We want to quickly update the model without needing to train the model from the beginning. So it's becoming increasingly clear that static algorithms are just not enough as a backbone for modern data analysis. So ideally, we would like to design dynamic versions for the previous problems. So in the sense that, and kind of the best, where the data matrix is changing over time. And ideally, kind of our dream would be to match the best static data structure for these problems, right? So this is kind of the holy grail of data structures, dynamic data structures in general. You know, the dream of dynamic data structures is that we can take any static data structure and dynamize it efficiently, ideally in a black box, in the sense that if we have a static data structure for a certain problem with Pn pre-processing time and Tn query time, then we could hope to, the best we can hope for kind of is to produce a dynamic data structure whose update time is roughly the pre-processing time over n, which is the amortized time spent on a single data point, and roughly preserve the query time, right? And we cannot really hope to do better because otherwise it's easy to see that we would produce a cheaper static data structure. So this is kind of the best we can hope for. Does that make sense? And in this question, I would like to answer the dynamization question specifically for these two algorithmic primitives. All right, so for the least squares regression problem, which, as we said, is a classic century-old problem, our goal is to produce the best least squares fit, or to find this cheapest hyperplane that minimizes the L2 loss. And we're, again, in the setting, the over-constrained setting, so there's no perfect solution. And you should think of D as, I don't know, something like root n throughout the talk. Right, so as probably most of you have seen back in your undergrad studies, this problem has an elegant closed-form solution, which is commonly known as the normal equation, which is simply whose geometric interpretation is just to take the vector B and to project it to the column space of A. Geometrically speaking, this is kind of intuitively the best approximation you can get, right? Just find the closest vector is just the orthogonal projection of B. And one way to see, to prove this equation is that we're just looking for the vector x, whose projection vector, so the difference B minus AX, is orthogonal to the column space of A, which by duality means that this difference vector, B minus AX, lies in the kernel of A transpose, and you just rearrange this bottom equation, and you get exactly the normal equation. Does that make sense? Question about this? So throughout the talk, we'll denote the actual solution, which is AX star by pi A. Pi A is going to denote the projection matrix onto the column space of A. All right, so despite the elegance of this equation, of course, the downside is that computing it is expensive. So it's super linear using naive matrix multiplication. Just producing, the most expensive step is producing the covariance matrix, A transpose A. This costs ND squared time using naive matrix multiplication. But even fast matrix multiplication will not save you in the case where the matrix is sparse, which is often the case, right? Especially with the advent of pruning techniques and sparsification, most data matrices are very sparse these days, either by nature or after pruning techniques. So the goal is to solve this problem much faster, ideally in input sparsity time. And to do this, a classic relaxation was considered, which is to settle for a small epsilon multiplicative approximation of the least square solution. Now we're willing to find, a solution which is slightly suboptimal, but we hope to do this, extremely fast. And this problem is kind of the classic, perhaps the classic application of linear sketching. In fact, the sketch and solve paradigm was born out of least squares regression. This was the motivating problem for the development of this entire line of work. And by now, it's kind of standard that one way to solve this problem is to take the original matrix, which is kind of huge, and compress it into a cheaper matrix, which has only roughly d over epsilon squared rows, where each row of A hat is essentially a random linear combination of the original rows of A, a plus minus one random linear combination, which is equivalent to multiplying A by a random Gaussian matrix from the left. Question? A hat is the data structure. So we are producing the data structure, and as we shall see, yeah, A hat is going to be unstructured and dense, yeah. But the important thing is it's short. It's unstructured, but it's short. And this is going to be important, and the classic Johnson-Lindenstrauss lemma guarantees that if we pick the number of rows of the sketched matrix A hat to be roughly D, which is the rank over epsilon squared, then A hat is a good spectral approximation. It preserves all the spectrum of the original matrix A. Does that make sense? And notice that we cannot hope for compressing the matrix below D, because then we would not even preserve the rank of the original matrix, right? And then the idea is to solve and to apply the same sketch to A and to the vector B, and then solve the problem using our favorite black box solver, which may be inefficient in the original space, but now we're applying it in the smaller space. So now it's going to become super fast. This is commonly known as the sketch and solve paradigm. It kind of decouples the problem, compress and then black box solve the problem in the lower dimension. And one thing you might hope for is that, the number of course, the efficiency relates to how many rows does the matrix A have. And as we said, we cannot hope to compress it below D, because then we don't even preserve the rank. But one unsatisfying thing is, notice the dependence of K on epsilon is polynomial here. So this would mean that we can only hope to solve the problem to within low accuracy, because otherwise the 1 over epsilon squared will kill us. And indeed, this was the original classic application, but in a long line of about kind of the past decade, it turns out that if you bootstrap this technique, if you combine linear sketching, not to directly solve the problem, but to actually precondition the matrix to reduce its condition number, and you combine it with the conjugate gradient descent algorithm, then you can really solve this static problem in kind of runtime which is as optimal as it gets. It's really, the dependence on epsilon is logarithmic, which means that it's a high accuracy solver, and it runs essentially in input sparsity time. So this is kind of as optimal as it gets. Does that make sense? Questions about the static problem? Yep. So conjugate gradient descent is something that is certainly being applied. Whether it's actually practical or not in modern applications, let's take this aside. But in principle, the nice thing here, notice we're not using any asymptotic Strassen methods or anything. We're really using numerically stable and you know, kind of purely, I would say, combinatorial techniques or spectral techniques. Okay, so going to the dynamic problem, so now our data sets or our least square linear system is evolving in an online fashion where, you know, each day another, you know, billion files are being uploaded to, you know, Dropbox server, and we need to retrain our model. We would like to avoid retraining it from scratch. So the setting is that the matrix and the labels are evolving in an online fashion, and our goal, of course, is to maintain pointwise, so for each iteration, not just in the final one, a small approximate solution for the teeth normal equation. So more formally, in the teeth iteration, the ith row is revealed along with its label, and our goal is to update the least square solution so as to produce a good approximate solution for the current iteration. Does the problem make sense? Yeah? So what's the naive way to do that? So suppose we have the actual, suppose we maintain by induction the actual normal equation for the teeth iteration. Once the new row arrives, the classic way to update this equation, which dates back to the 1960s of you know, control theory and Kalman filters, is simply to apply Woodbury's formula. So I hope most of you have been in yesterday's talk by Jan, where he explained that a rank 1 update to a matrix translates into a rank 1 update to the inverse of the matrix, right? So if you plug in, if you look at the covariance matrix, A transpose A, of the previous iteration normal equation, introducing a new row to A amounts to a rank 1 update to the covariance matrix, A transpose A. Does that make sense? And then we can use Woodbury's formula to update the normal equation or the inverse of the covariance matrix using this pretty formula downstairs here. The important thing about this formula is that there are many places where you'll pay d squared, right? Because it's a little confusing. A here stands for A transpose A, so it's actually a d by d matrix, right? So there are many places in this formula where you actually pay d squared time because you need to multiply a d by d matrix by d-dimensional vector. And therefore, the Kalman filter or Woodbury approach requires d squared time. Does that make sense? So to sum up, the clean and classic exact update time or for dynamic least square regression is simply using Woodbury's formula, and this costs d squared per time per update, which amounts to nd squared total time, right, over n updates, which is kind of back to the suboptimal solution or the slow solution we began with. Our main question in this work is, can we actually beat Woodbury, the d squared update time, in the dynamic setting, if again we're willing to settle for some small epsilon approximation? That makes sense? So we have, I'm going to present in the next 15 minutes 2 results which essentially settle the problem. The first one is that actually if we want a high accuracy solver, if we want a dynamic least squares data structure which maintains a high accuracy solution, so 1 over poly d, then actually the Woodbury update of Kalman filters from the 1960s is the best we can do. This is optimal under the OMV conjecture. All right, so the nice thing about this is that it's the first separation for this problem from the static and dynamic setting. Recall that in the static setting, we were able to get a logarithmic dependence on epsilon. So we had a very quick input sparsity time, high accuracy solver for this problem. Whereas in the dynamic setting, we're showing this is impossible under OMV. All right? On the other hand, if you're happy with a low accuracy solution with, let's say, 0.0001 or 1 over polylog n approximation, then you can actually achieve near linear update time in D. So you can quadratically improve the Kalman filter Woodbury approach. Do the statements make sense? So I'm going to spend the next 15 minutes proving mostly the upper bound, and then I'll sketch the lower bound. Questions until this point? And as an upshot, the upper bound, which was essentially the main idea was already appeared in a paper by Cohen, Musco, and Pachoki, and I think there was a typo in this paper, is not only fast in theory, it's actually practical. So we actually have simulation that actually works. All right, so let me start by sketching the upper bound. No puns intended. We want to prove that for the low accuracy regime, we can maintain a dynamic least squares regression data structure with roughly d polylog d update time, amortized. All right, so the first thing that comes to mind is, well, let's try to dynamize the static sketch and solve solution, right? And this actually suffers from one problem, which is that, remember, each A in the sketching data structure, each row of A hat was a random plus minus one linear combination of the original rows. And that is not a dynamic friendly feature, right? Because when a new row arrives, what does that mean? It means that on average, we'll have to update half of the rows of the original matrix. I mean, this new row of A hat depends on average on half of the rows of the original A. So the update, this would bring us back to d squared update time because, you know, it's d over 2 rows on an expectation, each of which costs d time to produce. So the real problem here is that the sketching-based solution based on the JL sketch is just not dynamic friendly. Does that make sense? Fortunately, there's a beautiful alternative technique to produce a spectral approximation to compress the matrix, which is not based on mixing of the rows, so linear combinations. It's based purely on subsampling. Okay, so it's sampling versus mixing. And this uses the notion of statistical leverage scores, which was, I think, you know, kind of long known in the statistics community, but brought to the TCS community by Drineas et al. In around 2012. So what is the statistical leverage score of the ith row of a tall matrix? There are several ways to see this. So the leverage score of the ith row is the diagonal entry, as you can see, of the projection matrix pi. Another way to see it is as follows. Take the matrix A, perform its SVD decomposition, and then look at the L2 norm of the ith row of the left matrix U. So we all know that in the SVD decomposition, the columns of the matrix U are orthonormal, right? But that doesn't imply anything about the rows, right? The rows are kind of arbitrary. And indeed, the L2 norm of the ith row is defined to be the leverage score. I know this is not very intuitive, so let me try to give a more intuitive explanation. The leverage score of the ith row of a matrix measures the sensitivity of the least squares solution to this row in the following sense. What would happen if we take this point and we remove it? How much leverage does this point have in pulling the hyperplane towards its direction? So how much would the least squares solution change if we remove this point? Does that make sense? So intuitively, if we have 1,000 copies of the same row in A, the leverage score of that row is very small. It's not going to affect the solution much, right? But if we have a row which is orthogonal to all the rest of the rows, then intuitively it's going to have a very large leverage score because removing this point is going to greatly affect the least squares solution. This is why it's called leverage score, because it kind of tries to pull the hyperplane towards its direction. Question? And we're going to rely on only two very clean properties of leverage scores. That's all we'll need, which is basically saying that leverage scores define up to normalization a probability distribution on the rows. So leverage scores are between 0 and 1, and they sum up exactly, precisely to the rank of the matrix. Why is that? Well, the second bullet is very easy to see. We just said that the columns of the matrix U are orthonormal, right? So the Frobenius norm of U is just the sum of the L2 norms of the column, which is D, because each column has norm 1. And now you can sum up the Frobenius norm by rows, right? And you'll get the same number, D. So the sum of L2 norms of the rows is equal to the sum of L2 norms of the columns, which is D. So the nice thing is that the sum of leverage scores is always equal to the rank of the matrix. Does that make sense? So here's the classic lemma that was proved by Drines et al. And when you think of it, it's not even clear, forget algorithmically, it's not even clear why such a primitive should exist. So for any matrix, let's say tall matrix A, you can always, there's always a sampling procedure with replacement and rescaling, such that if we subsample roughly d over epsilon squared rows with replacement according to the leverage scores, so where the ith row is sampled with probability proportional to its leverage score, then this rescaled subsample produces an epsilon spectral approximation to the matrix, exactly as in the JL sketch. Right? When you think of it, it's not even clear why such a thing should exist. All I'm doing is subsampling. I'm not doing anything else except rescaling. Right? So the claim to fame of this technique is that it's really dynamic friendly, right? Now we're only subsampling, and it really suggests a very clean dynamic solution, right? So here's what we'll do. When a new row arrives, AT, all we will do is we'll compute its leverage score, which seems expensive, but we'll take care of this in a second. And then we'll just, we'll compute its leverage score with respect to the maintained matrix, which is going to be close enough. And then we're just going to flip a coin. We're basically going to implement the leverage score sampling lemma in an online fashion. We're going to flip a coin. If the coin comes up heads, we're going to update this row using the Woodbury formula that Jan showed us yesterday. And otherwise, we're going to just throw away this row and never look back. We're just going to completely ignore this row. Does that make sense? That's it. That's the data structure. Okay? So one thing you might ask is, leverage scores are very expensive to compute. This is a d squared time operation, right? But fortunately, here we can use the JL lemma to compute this up to epsilon multiplicative approximation very quickly. Because all we're trying to do is preserve the L2 norm of a single vector. That we can do in, using log n over epsilon squared sketch. Okay, if this didn't make sense, just think of it as a black box. All we need to do is to compute the leverage score is to preserve the L2 norm of some fixed vector, and this we can do cheaply. And then the main claim here for correctness in the running time is the following invariant. I claim that the data structure maintains the following invariant, that the total number of rows that this data structure retains throughout those n iterations is always some d polylog d. All right? So what does this mean? Fine, when we invoke the Woodbury update, it's very expensive, at d squared to apply Woodbury, but we're only going to do this like d polylog d time. So when n is greater than, let's say, d squared, we're just amortizing away the Woodbury cost, right? So let me just touch upon how much time do I have? Like 10 minutes? So let me just sketch the invariant. I think this is the cutest part of the proof. So we're claiming that the sum of leverage scores, which is by the leverage score sampling lemma, exactly the expected number of rows that we keep, is never going to be more than d log d. So intuitively, what this means is the cost of dynamizing the leverage score lemma from the offline to the online setting is a mere cost of log D. That's all we're paying, and we get the online version, right? So first of all, I claim that if we compute leverage scores not with respect to the huge original matrix, but only with respect to the maintained matrix, D by D matrix, we don't lose much. And that just follows from the leverage score sampling lemma because it's a good spectral approximation. All we care is the spectrum. So I'm going to take a leap of faith from you guys on this one. And now I want to claim that the total sum of leverage scores with respect to the maintained matrix is never going to be more than d log d. So to do that, we're going to use a potential function, which is the log determinant, the log det potential. Okay, so for the teeth normal, for the teeth least squares matrix, when it arrives, I'm going to define its potential to be the log of the det of this matrix. And log det has a nice feature, which is that the log det of A plus a rank 1 update is super additive. It's at least log det plus U transpose inverse AU. So if you just apply this simple fact, where A is just the covariance, the teeth covariance matrix, A transpose A, and where U is just the ith row of A, the teeth row of A, the incoming newly arriving row, then you can take what is the potential of the teeth normal equation, the teeth matrix. You can apply this fact recursively. You just peel off using this log det lemma. You repeatedly apply it, and you get that this potential function is indeed an upper bound on the invariant we want to maintain, on the sum of leverage scores. This was a little quick. Did that make sense? I'm just applying this fact, iteration by iteration, and this is just for analysis purposes. And I showed you, I hopefully convinced you that the potential function is an upper bound on the invariant, the number of rows we keep. On the other hand, how large can the potential be in the final iteration? Well, the log of the determinant, we're looking at the determinant of a D by D matrix. How many terms does the determinant of a D by D matrix have? It has D to the D terms roughly, right? Like D to the D permutations. So log of that is roughly D log D. And that's it. That's the entire proof. I know I swiped a few details under the rug. What I convinced you is, and this potential function is really necessary because this only holds on a very amortized fashion, right? We never have control on a specific leverage score of a row. Does that make sense? And if you combine these two facts, you just get that, you just apply the expectation to both sides, and you get that the expected number of rows is never more than that. That's it. That finishes. Am I out of time, or I have 20 minutes more? 4 minutes. Okay. Okay. Life is full of surprises. All right, so let me just sketch the lower bound because unfortunately I won't have much time for that. So remember that the online matrix vector conjecture postulates that even over the Boolean semiring, we cannot multiply an arbitrary Boolean matrix by a sequence of n vectors faster than n squared time. Right? So well, our goal is to prove that under this conjecture, that if we have a too good to be true dynamic least squares regression data structure with high accuracy, so which maintains a high accuracy polynomial approximation, then we can break the OMV conjecture. Does that make sense? So how are we going to do this? The proof has 2 steps. The first step is to pass from the Boolean semiring to the reals, right? The least squares regression is solved over the reals. So our first step is to take this arbitrary Boolean matrix B from the OMV conjecture, which we wish to produce, to solve, and transform it into a well-conditioned positive semi-definite matrix, which is exactly this matrix here. We just take B and B transpose and put it on the anti-diagonal. And for reasons that are not important for now, I claim that this matrix is very well conditioned. It has a condition number of like 4 or something. And this ensures that if we have high accuracy matrix vector products with this new matrix H over the reals, then rounding will not kill us. It will produce the correct Boolean results over the Boolean semiring. Okay? If this doesn't make sense, just take it as a black box. Okay? So I claim that if we have a well-conditioned, high-accuracy solution over the reals, we can round it safely to a solution over the Boolean semiring. And the next step is to simulate the real-valued OMV using our too-good-to-be-true dynamic least squares solution. So when the teeth OMV vector arrives, we wish to multiply it, what we're going to do is perform the following update. We're going to we're going to feed the dynamic least square solution the following update, which is the same binary vector rescaled by d squared n. The rescaling is super crucial here, and this is why we get we need a high accuracy solution, because rescaling ensures that the difference between the least squares solutions in the teeth and t-1 iteration, the actual normal, the covariance matrix changes very, very little. And this is intuitively what we need, because in OMV, the left matrix is fixed, right? It never changes. So unfortunately, I don't think I have time to explain this, but if you kind of work out the details, you see that using Woodbury's formula, again, you just get, after rounding, the exact Boolean results, which breaks OMV. So any savings on quadratic time gets you OMV. Unfortunately, I have like probably 1 minute, so let me just say that in the setting of the fast multipole method, one might hope to dynamize it even under low rank settings, and this is, invite you to read our new papers on the fast dynamic version of a fast Gaussian transform. Let me just conclude that dynamic data structures are very important in modern machine learning and deep learning applications, especially if they're practical, right? And there are many more primitives we can explore. For example, everything that from yesterday's talk about preconditioning, sparsification, pruning. We would really like to see practical dynamic data structures for these problems. Another concrete question in the context of dynamic least squares regression is what happens in the fully dynamic settings. There, my conjecture is that you cannot beat d squared time even for approximate version, but I have no idea how to prove this. And perhaps another, maybe the most interesting question for me, which is not even about dynamic, is, assuming you believe the OMV conjecture, then we agreed we have to impose some structure on matrices if we want fast matrix vector multiplies. So the question is, what is the most general and most expressive, so to speak, structure that we can impose on n squared matrices, which nevertheless allows very fast, let's say n polylog n matrix vector multiplies. There's a nice paper by a Stanford group recently, like about 2 years ago, which postulates that butterfly matrices, which are kind of generalizations of FFT matrices, are kind of as general as it gets, but I have some, drawbacks for this lemma. So I think this is a super interesting question, and that's it. Thanks for your time.
Any quick question for Omri? All right, then I would like to let's thank Omri again.